Hi everyone. So the next section in our class is 5.2, and this is about the definite integral. So this section is closely related to the first section, 5.1, where we discussed the approximation of an area under a curve. So the goals of this section are the following. So first of all, we're going to define the definite integral and describe its notation. And then we're going to describe some integrable functions. There are actually many integrable functions, but we're going to describe only one class. And then the next goal is to describe the relationship between the area under a curve, or the area between a curve and the x-axis, and the definite integral. And later on we'll discuss properties. And at the very end we're going to discuss the average value of a function. Alright, so let me just start by reminding you how we approximated the area under a curve using the Riemann sum. So let me start by reminding you about the formula. So recall, so if you have a function y is equal to f of x, well, let's suppose that this is positive, at least for the graph, and then this function is defined on the interval a comma b. Then you can approximate the area under this curve. Let's say this is the function. So you can approximate the area under the curve by, let me first do this. So we can approximate the area by doing the following. We can take the Riemann sum f of xi star delta x, and the area is approximately this Riemann sum. So this whole thing is called the Riemann sum. Let me remind you that. And moreover, this is the length of a subinterval if you divide the interval a comma b into n subintervals, and this is the value of the function f at a particular point in the ith subinterval, and the product of both these two quantities gives you the area of one rectangle. So for example, if you have a rectangle like, maybe I should make a blue rectangle here. So if you have a rectangle like this, and this is delta x, then the height is f of xi star. Okay, so xi star is this xi star here is a point on the ith subinterval, and this is the length of a subinterval. Okay, so we did this in section 5.1. So basically we're saying that the area is approximately the Riemann sum. Okay, so if we make these rectangles, see, these rectangles here are made smaller and smaller, which means this delta x here becomes smaller and smaller, so the rectangles become very thin. Then the approximation of this yellow area here by rectangles will become better and better. So we were basically saying that as n goes to infinity, this is the number of rectangles, then the Riemann sum, this Riemann sum here, approaches the actual area. So let me write this down. So note, the more rectangles we use, the better the approximation. So as n goes to infinity, so this is a number of rectangles, we have that the Riemann sum, I should say I from 1 to n, f of xi star delta x approaches the actual area. Okay, this is the Riemann sum. Alright, so this is going to be the theme of this section. So basically this will give us the definition of the definite integral. So now let's define the definite integral. Alright, so let me start with the definition now. So definition, and by the way, this is the definition of the definite integral. Which is very important throughout this chapter. Okay, so let f be a function which is defined on a comma b. Okay, this is a closed interval. Then the definite integral of f from a to b, I should just say from a to b, is given by okay, so the notation is this integral sign, you put a and b, and then f of x dx, this is a definite integral, is equal to the limit as n goes to infinity of the Riemann sum. Okay, so this is true provided the limit exists. Okay, and if the limit exists, this function f is called integrable on the closed interval a comma b. So if the limit exists, the function f is called integrable over the interval a comma b. Alright, so the important language here, so the important terminology is the definite integral of f from a to b and integrable. Alright. Okay, so let's move on. Let me maybe first give you some terminology about this notation. I think I gave you some terminology last section, but let me do it again. So the terminology is as follows. Alright, so I have the integral sign, then I have the bounds of integration a and b, and then I have the function f of x, and then I have, let me use red color, dx here. Okay, so this is called the variable of integration. and this function is called the integrand. And these limits, these values a and b, are called the limits of integration or bounds. And the big S, is called the integral sign. All right, so let's do one example. So we're going to evaluate a definite integral for a specific function using two methods. Using this formal definition here, this formal definition right here, this limit, and also using geometry. Okay, so let me write down the example. All right, so let's evaluate the integral from 0 to 3 of the function 2x minus 1 using first the definition above, so the definition of a definite integral, then using geometry. Of course, for each part a and b, okay, for each of these parts we should find the same answer. All right, let's do a first. So using the definition, let's construct a Riemann sum. So basically we need to know what delta x is, what the xi's are, and so on. So let's do the following. So first of all, let me write down the function. So my function is 2x minus 1, and then the interval is 0, 3. Those are the limits of integration. And then we're going to use right endpoints and end rectangles. Now, of course, you can use any points in the ith subinterval or in the intervals, but right endpoints or left endpoints are the easiest version to do this, and they actually all give you the same answer, so let's just do right endpoints. Okay, so let's figure out now what delta x and all the xi's are. So delta x is equal to b minus a over n. So this is 3 minus 0 over n. So this is 3 over n. Okay, this is the length of each subinterval. And if we have the interval 0, 3, we want to divide that into n subintervals. So we'll do the following. So let's say that this is the interval of 0, 3. So 0 and then 3. So I'm going to divide this into subintervals. Okay, so the very first point is x0, the next one is x1, and then x2, x3, and so on. xn minus 1, and the last one is xn. Okay, now the right endpoints for the first subinterval, x0, x1, the right endpoint is x1. Then for the next interval, x1, x2, the right point is x2, and so on. So basically, the right endpoints are x1, so x1, x2, x3, xn minus 1, xn. Okay, so all those points are the right endpoints. Let's find their value. So x1, but let's start with x0. So x0 is just 0, right? And x1 is just 0 plus 1 copy of delta x. And delta x is 3 over n, so this is 0 plus 3 over n, which is 3 over n. And then x2 is 0 plus 2 copies of delta x, so this is 2 times 3 over n. You keep going like that, so xi is equal to 0 plus I times delta x, so this is I times 3 over n. And the very last one, which is xn, is equal to 3. Okay, so these are, maybe I should highlight these. So these are the right endpoints. Maybe I should highlight them with blue. See if I can do that. Okay. So now let's construct the Riemann sum. So the area according to the definition of the definite integral, maybe I should say the definite integral and not the area. So the area, which is a definite integral from 0 to 3 of 2x minus 1 dx, is the limit as n goes to infinity of the sum I from 1 to n. I'm going to use the right hand point, so xi stars are just xi and delta x. Okay, so this is equal to the limit as n goes to infinity. You have the sum I from 1 to n, f of, now xi is 3i over n, so I should say 3i over n, and then delta x is 3 over n. That's delta x. Okay, so times 3 over n. Now we have to plug in 3i minus 3i over n into the function, and our function is this. So just plug 3i over n into x here. Alright, so then you have the limit as n goes to infinity of the sum I from 1 to n of 2 times 3i over n minus 1 times 3 over n. Now 3 over n, so by the way, let me just emphasize something here. The thing that's changing in the sum here is only I. So I changes from 1 to n. So n is fixed for now. Forget about the limit for a moment. N is fixed, okay? After you find the sum, then you take the limit. Okay, so let's first find the sum. So this is equal to the limit as n goes to infinity. Now since I and n are independent, you can take this 3 over n here and put this in front of the sum. So I have 3 over n, the sum I from 1 to n. 2 times 3i is 6i over n minus 1. And now you can split this into two pieces. So this is the limit as n goes to infinity. 3 over n times, you have the sum I from 1 to n, 6i over n, minus the sum I from 1 to n of 1. Okay, the sum of a difference is the difference of the sums. Okay, so this is equal to the limit as n goes to infinity. You have 3 over n. So now again, since 6 and n have nothing to do with I, you can bring 6 over n here in front of the sum. So you have 6 over n times the sum I from 1 to n of I minus, now this sum here is just 1 n times, so 1 plus 1 plus da 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 plus 1, so this is just n, okay? And this sum here is 1 plus 2 plus 3 up to n, so that's equal to n times n plus 1 over 2. I don't know if you know that one, but you don't have to worry about it right now. So this is equal to the limit as n goes to infinity, 3 over n, and then you have 6 over n times n times n plus 1 over 2 minus n. So keep going. And this is equal to the limit as n goes to infinity. Now you can multiply things out. So you have 3 times 6 is 18, n times n is n squared. So you have 18 over n squared times, now this part here is n squared plus n over, actually you can just simplify, so let me go back. I want to keep it as n times n plus 1 over 2 minus 3 over n times n. Now you can simplify some things. You can simplify this n and this n, this n and n here. So you have the limit, by the way I need the parenthesis here, as n goes to infinity, you have 18 over 2 is 9, so maybe I should also simplify this. So you have 9 times n plus 1 over n minus 3. This part here approaches 1, so this is equal to 9 minus 3, which is 6. So long story short, the integral from 0 to 3 of 2x minus 1 dx is 6. Now this is using the definition. Alright, so now for part B, let's use the geometry behind this. So let's use geometry. Alright, to use geometry, we need to basically interpret the integral as the area, because the limit of the Riemann sum as n goes to infinity, according to the definition, is the area, right? So let's first draw the graph of 2x, y is equal to 2x minus 1. So if you plug in, so I have the function y is equal to 2x minus 1. So if you plug in x equals 0, you get negative 1. So let's say negative 1 is somewhere here. And when x is equal to 3, y is equal to 2 times 3 plus minus 1, which is 5. So 3, let's say that this is 5. This is the value of the function. So this is a line, so I have to just join these 2 points. So the area that we're talking about, which is the integral from 0 to 3 of 2x minus 1 dx is equal to, and this is, so I have to be careful here, this is this blue area, let me, okay, plus this pink area. Okay. All right, so let me just say this is the blue area. Let me just say the total area with signs. Okay, now this blue area here is negative. Since the values a value of the function are is negative there. Okay, and for the pink one, the area is positive because f is positive. Okay, so to find this area geometrically, we have to find this area here and put a negative sign, and this area here, and then add them together with signs. All right. So this integral is equal to minus the blue area plus the pink area. Okay, so what is that? So the blue area is equal to, now this side, by the way, if you want to plot this point here, this is exactly when y is equal to 0, so that x is 1 over 2. So the blue area is minus 1 times 1 over 2 divided by 2, so times 1 over 2, plus the pink area is 3 minus 1 over 2 to find this difference here, so the base, so that's equal to 3 minus 1 over 2 times the height, which is 5, and divided by 2, so we have to divide by 2 as well. Alright, so this is equal to negative 1 over 4. 3 minus 1 over 2 is 5 over 2, times 5 over 2 is 25 over 4. So this is 24 over 4, which is 6. So using areas, which means using geometry, you also find that this area is 6, which should, that's the answer, so it shouldn't be any different. All right, so right now we have two methods to use the definition and to use geometry. Let me just say that using definition is usually very hard, while in general, this is hard. If you have, for example, higher degree polynomials, it's fine, but if you have, for example, trigonometric functions, exponential functions, etc., it gets very complicated, so we're not going to use this. But the geometry is actually very limited. So later on we're going to discuss the fundamental theorem of calculus, which is going to reinterpret all of these integrals in terms of antiderivatives. So let's move on and leave it for later. Okay, now since we talked about negative areas and positive areas, we have to think of definite integrals as net signed area of the region between the function and the x-axis. So let me make that definition. All right, so definition. So I have two definitions here. Now, first of all, the net signed area is equal to the integral of the function, the definite integral from a to b of f dx. So this is basically the net area between f and the x-axis. Okay, but the total area, which means if you count all areas as being positive, regardless of them being below the x-axis or above the x-axis, so that's called the total area. Again, between Oops, I don't need this part here. Let me erase this part. So again, between f and the x-axis. So this is just, again, almost the same thing, but you have to add something to that. So we have to take the absolute value of the function f. Okay, that's the only difference. So this is basically the net area versus total area. Okay. And we'll use this later when we do some applications with motion. Okay, so maybe I should do one application right now, since it's related to this definition. Okay, let's do the application. Okay, so let's suppose that an object is moving in a straight path. We're going to drop the units. So let's suppose that an object is moving in a straight path with velocity v of t is equal to t minus 2 for the time interval, let's say from 0 to 6. Now the first question is, find the displacement of this object during this time interval. Okay, so basically this means the following. Find the total area with signs for the graph of this function from 0 to 6. So let me explain what this means. Okay, so I have the graph of the function. So this is, let's say this is negative 2. And let's say that, so this is 0. Let's say that this is 6. And this is the t-axis, and this is the velocity axis. Now, our function is v of t is equal to t minus 2. So when t is 0, v is negative 2. And when t is 6, v is, when v is 6, t is 4. Okay. Right, so you plug in 0 for t, 0 minus 2 is equal to negative 2. And then you plug in 6, so 6 minus 2 is equal to 4. Okay, so this is 4. Velocity is equal to, normally, this is just a quick argument. So velocity is equal to distance over time, right? So v times t, so velocity times time should be distance. So if you want to find distance, you have to multiply v by t. But if you multiply v by t, you find areas in this graph. So this is basically talking about the area between this line which is the graph of the function, and the t-axis in this case. So this is the t-axis. So basically we're talking about this area right here and this area right here. So let me highlight them. So I'm going to use these colors again. Okay. So let me use yellow for this other one. Okay. I'll just be quick. Okay. So that's it. So now we have the green area as the blue area and the yellow area. Now again, since we're finding displacement, which means how far you went from the initial position, we have to consider these areas with signs. So this is now a negative area because it's below the t-axis, and this is positive area. Okay, so whenever an area is below the t-axis or the x-axis, it's negative. Whenever it's above the t-axis or the x-axis, it is positive. Okay, so now we just need to find the net signed area, basically. So the displacement is equal to the net signed area, which is equal to the integral from 0 to 6 of t minus 2 dt. Okay, so this is equal to the following. So you have first this blue area here. So this here is the point when v is 0. Okay, so basically t is going to be 2 there. So this is 2. Okay, so the blue area is negative 2 times 2 over 2, that's a triangle, plus 6 minus 2, which is 4, times 4 over 2. So this is basically equal to negative 2 because these cancel, and this also cancels that, so this is 2, plus 8, so this is 6. So the displacement is 6 units from the initial position. Now if you want to find the distance traveled, which is part B, you have to consider both areas as being positive. Okay, so let's find the distance traveled. Let me copy this graph here because I need this. Okay, copy and then paste. Okay, so now in this case both of these areas should be positive. This is also positive. So you have to count for both distances traveled, even though they are negative in this picture, they should be positive because even if you go backwards or forward, the mileage is the same. Think of the distance traveled as the mileage of your car. So it doesn't matter which direction you go, the mileage is still going to go up. It never decreases, right? But if you go forward and then backward to the same point, your displacement is 0. That's why in part A, we treated some of the areas as negative. All right, so in this case then, you have that you have to find the integral from 0 to 6 of actually the absolute value, of the absolute value of t minus 2 dt. So this is the total area, okay? So this is equal to 2 times 2 over 2 plus 6 minus 2 times 4 over 2. So this is now 2 plus 8, which is 10. Okay, so this here is positive. Whereas in the previous part, this was negative. Okay, that's the difference between the two. All right. Okay, I hope this is clear. So then we're just kind of made a general statement here that in general, we have that displacement is equal to the integral from a to b of the velocity function dt, but the total distance traveled is equal to the integral from a to b of the absolute value of vt. Okay, so keep that in mind. Now let's talk about some properties of integrals, which we're going to use very often. So let me list them. I should say definite integrals here, even though these are also for indefinite integrals, but let me make the distinction for now only. So this is definite integrals. Okay. Okay, so the first property says that if you integrate on a point, so from A to B, from A to A, so basically you don't move on the x-axis at all, then the integral of any function, as long as this function is defined on A, is equal to 0. Okay, that should be very clear because there is no area of a line segment. And then 2, the integral from A to B of f of x dx is equal to, if you switch the limits of integration, then you have to put a negative sign. Okay, so note here that A moved up here and then B moved down here. That's why you have to have this negative sign in front. Okay, so the third property says that if you integrate the sum of two functions, so f of x plus g of x dx, this is the same as the sum of the integrals of f and g. And the same is true also if you subtract the functions. So the difference, the integral of a difference is the difference of the integrals, and the integral of a sum is the sum of the integrals. Number 4, if you take the integral from a to b of a constant c times the function f, you can always pull this constant in front of the integral. So this is equal to c times the integral from a to b of f of x dx. And then 5, if you integrate a function from a to b, and you know that there's some c between a and b, okay, so let me say there is a c here, somewhere here in in between a and b, then you can split your integral into two pieces. So you can say that this is equal to the integral from a to c of the function plus the integral from c to b of the function. All right, so let me give you two examples. The first one is an example I will not really solve, it's just I'm going to show the properties on the example. So the integral from 2 to 7, for example, of negative 3x to the power of 4 plus 5x minus 10 dx is equal to the following. So you first split this into three integrals, the integral of this term, and then this term. So I have the integral from 2 to 7 of negative 3x to the power of 4 dx plus the integral from 2 to 7 of 5x dx minus the integral from 2 to 7 of 10 dx. So this is equal to, now you can pull these coefficients outside of the integral. So I have negative 3, the integral from 2 to 7 of x to the power of 4 dx plus 5 times the integral from 2 to 7 of x dx minus 10 times the integral from 2 to 7 of 1 dx, and so on. So you can always use these properties. So let me do another example. Maybe I should start here. Okay, let's suppose that the integral from 0 to 8 of a function f is, let's say, 10, and the integral from 0 to 5 of the function is 3. Let's find the integral from 5 to 8 of the function. Okay, so we're going to use, so maybe I shouldn't, so you shouldn't confuse, let me move this a little bit here. These are separate, okay, don't confuse the 2 and the 5 there. Okay, so let's use property number 5 now. Okay, so we're going to use this property to solve this question. All right, so we know that property 5 implies that the integral from 0 to 8 of f is the integral from 0 to 5 of f plus the integral from 5 to 8 of f. Okay? Now since this part here is given, this is 10, and this part here is given, it's 3, then you can say that the integral from 5 to 8 of f is just 10 minus 3. This is 7. So it's that easy. Okay, just by using property number 5. Okay, I hope this is clear. Now let's move on to a couple of more comparison properties for integrals, and then we're going to define the average value of a function. Okay. So let me just call this the comparison theorem. For integrals. All right, so this theorem says the following. It has three statements about comparing the values of various integrals. So the first one says the following: if the function f is greater than or equal to 0 on the interval a comma b, then the integral from a to b of f is also greater than or equal to 0. Alright, the second property says that if f is greater than or equal to another function g on this interval a comma b, then the integral from a to b of f is greater than or equal to the integral from a to b of g. Okay, and the last one is the comparison between two constants bounding a function. So let me just suppose that I have the following. So if little m is less than or equal to the function, and the function is less than or equal to capital M on this interval a comma b, then the integral of this function f is less than or equal to and greater than or equal to two specific values. So on the left, let's say we have lowercase m times b minus a. And then on the right, you have capital M times b minus a. Okay, now this might seem like a weird thing to say, but let me describe this on a picture. Okay, so let's suppose that we have a function f. Okay, and let's say this is our function. Now the smallest value of the function is this value here, right? And the largest one is this value here. So then we can just say that this here is little m. So if I extend this, I have that. And this value here is capital M. Okay? Then this theorem here, let me make also a box here. Okay? Now this statement number 3 says that the area under this curve, the area under this curve here is, so basically this area here is bigger than this area here, which is given by this value, but smaller than this area of this rectangle, right, which is given by this value. So let me highlight them. So okay, maybe I just use the pink one. So the pink one, maybe I should start with the blue one. So the blue one is for this side. Okay, so let me emphasize this. Oops, sorry, I need the smaller version. Okay, so this value here is, this area is this value, right? And let me highlight in yellow this part of the area. Of course, let's suppose that this extends down, okay? And then the big area is this area here. Of course, you have to go all the way down, okay? So the pink area is all of this area. I don't want to highlight on top of each other. And that's the bigger one, and the smaller one is this area here. And the smallest one is this area here. Okay, so that's a statement of this property number 3. Okay, we're not going to use them right now. We'll use them later, but let's keep that in mind. Okay, so let's discuss about the average value of a function. All right. So the average value of f. So if you have a function, then we are going to define a way to find the average of this function. Now, if you have a bunch of numbers, the average of those numbers is just adding them up and dividing by the numbers of values you have. So for example, if you have a1 plus a2 up to, let's say, a10, then the average is a1 plus a2 up to a10, all divided by 10, right? Now, how do you do this for functions? So what about functions? All right, now here's the definition. Of course, we're not surprised if we use integrals, right? So the average value of f on the interval a comma b is defined by the following. So f average is equal to the integral from a to b of the function. Okay, so maybe I should write this a little better. Okay, so b is here, of the function dx, and then you have to divide by the length of the interval, which is b minus a. So that's it. Okay, so the average value of the function is given by an integral divided by some number. Okay, so let me show this to you on a picture. So for example, if you have a function, let me just draw a generic one. Say this is a function. Okay, this is a and this is b. Then what this definition is saying is that the average of the function on this closed interval a comma b is this integral. By the way, this integral here is this area, right? Divided by this length. This is this length here. Okay, so let me first highlight this area. I guess I'm starting to like this. Okay, so this is the area I'm talking about. Okay, and instead of having this area, we're going to interpret this area, the yellow area, this area right here, as the area of some box, like that, okay? Because if you divide this area by this, you'll find some number, which means if you multiply that number by this length, which is a base, you'll find the area of a box, which is also the yellow area. So basically what this is saying is that this yellow area is approximately the area of this box. So I'm just trying to guess here now that if you take this box here, this red box has the same area as the yellow region. So this value here is the average value, okay, which is the height of this box. So let's do one example. I hope this is clear. Okay, let's find the average value of this function. So x plus 1, on the closed interval 1, 5. Okay, so let me first draw the graph. So I have the following. So this is just a line. So basically, let's say that this is 2, and then 4, and then 6. So this, when x is 1, 1 plus 1 is 2. So basically, if x is 1 here, then y is 2. And when x is 5, 5 plus 1 is 6. So let's say this is 5, and 6 is somewhere here. So this is a line segment. Okay, so the value that we're looking for, so the average value, by definition should be 1 over, so this is the definition right here, 1 over b minus a times the integral from a to b of the function. So this is equal to 1 over 5 minus 1 times the integral from 1 to 5 of x plus 1 dx. So this is equal to 1 over 4 times. Now we need to find the area of this region here. So you can split this into two pieces. By the way, this is 6. So you have first this rectangle here, the yellow rectangle. And then you have the blue triangle. Okay, so the blue triangle, let's start with the rectangle. The yellow rectangle has size 5 minus 1 is, 5 minus 1 is 4. So 4 times 2, that's the yellow rectangle. Okay, plus the area of the blue triangle should be 4 is the base times the height is 6 minus 2, which is 4 over 2. So this is equal to, by the way, this 4 cancels this 4 and this 4. So this is basically 2 plus 4 over 2 is 2. So this is equal to 4. So the average value of this function is 4. And that's it. So that's all I had to say about this section for now. So see you in the next section. Bye.